This video is for the groups that are investigating the effect of concentration of hydrochloric acid on the rate of the chemical reaction. So in this lab, you will be using hydrochloric acid as one of your reactants, and the concentration that's given to you will be called 1M. That will be the starting concentration, or C1 as it's written here. Now M stands for the unit known as molarity, which has to do with the amount of acid that's in a given amount of the solution. So technically it means the moles. There's a unit called a mole, which we'll learn about. The moles of the HCl per liter of the solution. Okay, but it's not going to be important for you to break down what the M stands for. It's just important that you understand that the M, how many M are in there, has to do with how concentrated that acid is. And concentration is about how crowded together are the particles that are in that solution. Okay, so if we make something less concentrated, then the particles are more spread out. There's more space between them. If we make something more concentrated, then there's more particles in the same amount of volume, in the same amount of space. And that has an influence on reaction rate. So as an example, I've made up a simple one. It's easier to see if we do it with something that has a color. So this is just food coloring in water. Now, I've added 10 drops of food coloring into, let's say, a liter of solution. So I'm going to call my concentration 10D instead of M, because I'm talking about drops. So if I'm investigating concentration, I'm going to need to outline at a minimum 5 different treatments. That means 5 different concentrations. So I've come up with that if this was my investigation, I would use the original solution, this one, which we've said has a concentration of 10D, 10 drops per liter. So we'll just call it 10D from here on out. And then I would use 4 other concentrations that are lower, 8, 6, 4, and 2. I've chosen those because they're kind of evenly spaced out, and they give me a pretty good range from 10 all the way towards 0. Okay? So notice that all we are doing is making them less and less concentrated. And the way we do that is by adding water and diluting them. But we want to be able to do it in a very precise way so that we can actually get the concentrations of 8, 6, 4, and 2. So the rest of the video will be to show you how to do that. Before you do that, you need to think ahead a little bit and think about how much you're actually going to use in your lab. Now, as a made-up example, you may not use 20 milliliters in each of your trials, but I've chosen that amount for this example. So if in every time that you run the reaction and you record the pressure change, you want to use 20 milliliters of acid, and you decide that you're going to do 5 repeated trials, that would mean that in total, you would need 100 milliliters of the 10D solution, the 10D concentration. But it would also mean, if you did that for every one, and you did 25 trials total, you would need 100 milliliters of all of them. So you might have a different volume per trial that you decide on, a different repeated number of trials, and a different total volume. But this is what you need to think through in advance. How much do I need to make? So in my example, I am going to need to make 100 milliliters, and I'm going to do an example to make the 2D solution. So I'm starting with 10D, and I want to dilute it down to 2D. So I want to go from 10 to 2. So I want to decrease its concentration by a factor of 5. So how the heck do I do that? Well, there's an equation for dilution. C1V1 equals C2V2. So the C values stand for concentration, and the V values stand for volumes. What I care about is how much of that original red solution do I need to measure out in order to make the new concentration. So what I'm going to do is I'm going to solve for volume of the original solution. So I start out, these C1 and V1 are about that original 10D solution, and C2 and V2 are about the new solution I'm making. Now I'm rearranging the equation. I'm dividing both sides by C1, and that cancels it out from the left-hand side of the equation. Those will cancel. And I'll end up with volume 1 equals C2 times V2 divided by C1. Okay, let's see that in practice. So I've just rewritten the equation here. So in the example I said I want to make the 2D solution, and I want to make 100 mLs of it. So that's why I need to know the volume in advance, 100 mLs. I'm starting with 10D solution. So I plugged in what I want to make on the top is C2 and V2, the new concentration and the new volume. And on the bottom, I plug in the original concentration. Well, 2 times 100 is 200, divided by 10 is 20. So this equation tells me that what I need to do is measure out 20 milliliters of my number 1 solution, my original 10D solution. And then I'm going to add water to it until I get to 100 mLs. So let's see that in practice. So this is what's known as a measuring cylinder. Okay? And I've used this to measure out 20 milliliters of that original 10D solution. So I poured it in, yada, yada, yada. I poured it in and I measured carefully that I had 20 mLs. So that's a really good device to measure out a small volume. And then we have these other devices called volumetric flasks. Now these are actually really good, more precise at measuring very certain volumes. So I decided I'm going to measure 100 mLs total, so I'm going to use this 100 milliliter volumetric flask. We also have ones that measure to 250 if that's what I needed, but I need 100. So how do I go about doing this? Well, the first thing I do is I fit my volumetric flask with a funnel because it's got a very small neck. I'm going to slowly add that 20 mLs that I measured out. And then the rest of the way, I'm just going to use water. So you pour slowly when you use the funnel. If you pour too fast, it'll probably overflow. Now, if you go really careful, and you can see that at the top of this one, there is a little line. Okay, there's only one line on a volumetric flask, and that's the line we want to measure to. Now, I was doing this while holding my camera, so I went a little over, which is a big no-no, but you'll forgive me. That's the idea. I can put the cap in, and then I can turn it upside down once the cap is in, and that will help mix it up. And now, if I come over here and put it, so now you can see the solution that we made, this lighter one that looks almost orange, is far less concentrated than the one on the left. So the original one has a concentration of 10 drops per liter, and then we made 100 milliliters of a 2 drop per liter solution. So this one has a concentration of 10, and this one has a concentration of 2. And so that walks you through how you can calculate based on the original solution you're using and what you want to make and how much of it. Tells you how much of the original solution you need. You measure that out first in a measuring cylinder, and then you can use a volumetric flask to help you get a precise final volume of something like 100 or 250 cm cubed. And then you can repeat that process. You'll use different amounts of the original solution to make the other concentrations that you were trying to make for varying and getting 5 different concentrations, 5 different treatments for your independent variable.